All right, thank you very much for the introduction and thank you for the invitation. Um, so I just gave a talk on multimodal workshop. Thank you for being here among, there's so many workshops to go to. So at the multimodal workshop, I talked about our like bi-inspired robots. Here I'm going to talk about our soft morphing based on origami principles. Um, so I'm sure many people, I think this is something very obvious from you're going from structured environment to unstructured environment, right? So to go into the unstructured environment, like household, and we need more interactive robots, and safety becomes very important. And so this is something that in our communities, in soft robotics community, we always talk about safety, adaptability, and all those kind of things. And for me, I'm sure like shape morphing means different things for different people. For me, shape morphing, it's about spatial efficient form factor when not in use. So in this talk, I'm going to try to talk about that. It also means adaptive behavior as well. But so this is the video animation from Big Hero 6. I'm sure you know Baymax, but I'm pretty sure not many people recall that Baymax starts out from a box and then becomes pretty big. If you think about it, well, you're at home or you want to carry this around, you want spatial efficiency, right? So that's why we are interested in using morphing as a concept to be applied to soft robots. So for better human environment and robot interaction, we need, we put payload here because one of the drawbacks of a soft robot is that the payloads are low. But in order for soft robots to be practical, I believe that we need to have higher payloads. Safety is something that's obvious. Space efficiency, I said is important. Workspace is also something that's important. We need to get large workspace. Also, lightweight will be an important factor if you want to carry this around and so on. So as I already showed you, Big Heroes from this was our starting point of our work on this area. And if you think about the shape morphing in nature, this is the blowfish. Right? So blowfish actually changes its shape, actually to scare out your enemies, right? But compare that with pelican eel. So this is a pelican eel that lives deep under the sea. It starts out very slim, like an eel, and then it becomes really big, much bigger than the blowfish. How does this do this? How does it do this? Blowfish uses single morphing, just stretching, whereas pelican eel goes dual morphing, meaning it sort of unfolds the structure and then it stretches out. So this is our concept. So we are trying to make use of the dual morphing concept of the pelican eel, where first morphing is for shape formation, so geometric translation, basically. You change the geometry of the robot. And then the second morphing is for stretching. It's based on stretchable skin. So if you combine the kinematically deployable frame with a stretchable skin, then you can get a very extreme shape morphing through dual morphing of the unfolding and stretching. So we actually built something that looks similar. So two design methods. So dual morphing. So as you can see, it unfolds and then it stretches. So that's how it goes. So as you increase the pressure, normal soft robots would go like this. Origami, kinematically shape changing will go like this. If you combine those two, you're gonna go more into a linear deployment. You can think of this as an asymmetric lengthening because first you have the linear deployment and then you have the bending. So if you do this, then you're gonna be able to see. And our approach is to create a unit cell. It's an origami unit cell. It's a combination of unfolding with a new net. So I'm sure all of you know about the new nets. So new net it has chambers with which can like stretch. So if you combine these two concepts, then you get a stretchable origami unit cell. We call it origami unit cell. So which can undergo unfolding and stretching. So this is what's going to happen. So we are doing a tensile test of this origami unit cell. And with this origami unit cell, what we can do is now we can combine this with the concept of origami, because now you have like Mira Ori. If you want to use the Mira Ori pattern, you use this unit cell to do the Mira Ori. You can do like origami fish base. You can do Yoshimura Ori pattern. So just basically use that origami unit cell, and then now you can come up with all different designs based on origami. So we did like Mira Oris origami, fish base. We already showed you the fish base and this origami. So sequential motion design, unfolding, it goes through the origami shape changing, and then it goes through the stretching. So this is what happens if you start applying air pressure. Actually, the linkage actually opens up, and then after the linkage opens up, if you put in more pressure, it's going to stretch and it's going to start bending. So here is the pattern. So okay, so you apply the pressure, it goes to the deployment, and then because of the asymmetric lengthening, now this is the first path, and then the second path is going to the bending. So deploy and bend. So that's the asymmetric movement that you see. So this is the paper Mira Ori fold, the Mira Ori polyhedron, and this is the Mira Ori origami. So this is a simulation, and this is the actual thing. And as you can see, you start from a very compact soft robot, and then you can build a large soft robot. So this is a dual morphing, and actually, so this is a conventional unit, right? Conventional units are just bending. It's not changing the whole shape. So we are trying to define the morphing into two different types of morphing: kinematic-based morphing and stretching-based morphing. And this is a response to the applied pressure. And so sequential deployment, so linear deployment and bending, right? So the first path is the linear deployment. Second path is the bending. So that's what you see. And you can actually design the second morphing. What I mean by design of the second morphing is by changing the stiffness of the segments of the material. Now you get different kinematics, right? Imagine you have high stiffness portion in this area and low stiffness portion in this area, then you will get this kind of kinematics. If you have same stiffness, then you get this kind of kinematics. If you switch from stiff to high stiffness to low stiffness, then you get this kind of shape. So you can play now. You have the kinematics normally is based on the linkage shapes, but in soft robotics, just by changing the stiffness of material, you get different kinematics. So this is the characterization of the first morphing. So origami unit cell. This is fluid-driven origami model. It unfolds and stretches. So unfolding and stretching. And this is what's going to happen. First path can be designed by changing the origami kinematics, right? So if you want to change this first path, instead of this path, if you want to go to this path, you can do so by changing the length of the segments. Right? By changing the angle, you can change the angle of the parallelogram, and you can change the length of the segment. And just by changing this alpha, you're gonna get different theta. So you can see here, as you apply the pressure with different alpha angle, 50 degrees to 80 degrees, you're gonna see different theta angles appearing. So this is one parameter of changing the kinematics. So width of the crease lines is another parameter. So by changing this width of the crease lines, again, if you see here, by changing the width of the crease lines, you're gonna get, depending on the pressure, you're gonna get different kinematics. So you can see that this unit cell, by playing around with these kind of parameters, now you have more freedom of creating different workspace out of this single cell, right? The alpha and the omega. So I mean, compare this with when you learn robotics, right? Kinematics. It's all about theta 1 to theta 6, and that's how you create. And then of course the length of the linkages. That's how you create different kinematics. Soft robotics, now you have more parameters to play around with. This is for this design, but I'm sure you can do this for many other soft robot designs. You have to choose which parameter that you can change to generate different kinematics. And the characterization of the second morphing stretching, it's going to depend, again, second path will be designed by changing the material stiffness. So here I already showed, explained by, if you have an inner bend, if you have a inner side lower, you have a E1 to be lower stiffness and E2 to be higher stiffness, then you're going to get an inner bending. To get an outer bending, you switch the stiffness ratio. So again, it's not just the kinematic parameters, but it's the stiffness parameters that you can play around with to change the kinematics of soft robot. So characterization of the Origami module, it's unfolding and stretching. And as I said, we have two types of morphing and two types of parameters. One is the geometry parameters, which can change the kinematics of origami. We played around with alpha and W, the width of the crease line, and also by changing the material parameters, you can basically change the workspace of your robot. So with that, we created several different types of applications. So this can be hidden, and then you can come out and catch a crawling robot. I presented that robot, similar to that robot, in my previous workshop. And then you can also, it can be a deployable soft crawler, right? You can have, imagine you have like hundreds of these, right? You want to be able to pack them into a lower, smaller area, smaller volume, and then like deploy them, right? Then it becomes a crawler. Not exactly the Baymax, but soft-hugging robot. And this is also a like inside the water, right? You can start from here, and then you can do the underwater robotic eye tentacle. And so Yoshimura pattern. So this is a Yoshimura pattern, and we can also do Yoshimura pattern. So similarly, you have first morphing and second morphing. So first morphing, you can change the parameters, kinematic parameters. Second morphing, you can change the stiffness parameters. Here we show that just by changing the stiffness, we get different types of kinematic motion. And we created a Yori soft caging gripper. And you can see that this, it undergoes a linear deployment, and then after that, it goes through this kind of buckling transition, basically shape changing. And with that buckling transition, you get a very high force, grasping force out of this Yoshimura pattern. So you can use it for these kind of different applications. And the deployable, so we started playing around with the idea of having a new net that can be deployed. So if we can design the unit chambers using Yoshimura patterns. So imagine if each chamber is a Yoshimura pattern chamber. Now you can start with a low profile actuator, which blows up, and now you have a higher moment arm. So your higher moment arm means higher force, right? So you can, so what can you do with this? If you can create a glove, right? So there was this kind of Harvard had formerly built this kind of glove. You can build a glove out of this, and if you're not using it, it'll be flat and wearable. And by having different dragon skin, you will have different kinematics. And what we showed here is that with the weight of the robotic glove can hold around 1 kilogram with about 20 kilopascal. So if you see this video, so as you see, initially it's flat, and then it expands. And if you need, so what's going to happen is, if not much force is required, it's not going to be blowed up a lot. But if it requires larger force, then it will As you pump in more pressure, the height will increase, and you'll be able to get higher grasping force. Okay. Fabrication is sort of an issue because we need a very complicated mold to do this. So this is how we have designed the mold. So this is a magnetic modular mold assembly. So we go through this process to build several layered molds because we need to create those folding lines. To create those folding lines, we need this kind of a more complicated molds. And so so we've been using stretching, but stretching has some issues. For example, if we're using highly soft silicons, stretchability is large, but there are drawbacks like the Mullin's effect, which is like hysteresis effect, and the force cannot be very high because it's stretchable. Response will be pretty slow, and one of the biggest issues is the fabrication. And there are like low stretchable fluid driven actuators coming out. Probably the paired, these pouchy motors. Ryuma started this, but many other like SKKU is also working on this. Hazel actuator is basically it's a less stretchable actuator. So if we utilize flexibility instead of stretchability, we might get away with getting a similar performance, but without too much of a stretchable material. So our concept here is to use two different types of Miraori. So one is a Miraori polyhedron, another is a zigzag Miraori. If you superposition the two origami structures, then it becomes a dual origami structure, where it undergoes a asymmetric lengthening because this polyhedron will lengthen, and that zigzag for the Miraori will actually limit the length of one side, which will actually bend the actuator. So with this, then what we are able to do is we can actually get this kind of dual morphing without using a stretchable material. And because we're not using a stretchable material, what we can do now is 3D print. If you can 3D print a soft robot, then you have a lot more freedom in designing. So we can compare the dual morphing design with dual origami design, and of course, the deployment ratio of the dual morphing design will be higher, but force will be smaller. Your origami design will have a smaller deployment ratio, but the force will be much higher. So this is the comparison. And we've actually modeled the dual origami actuator. And with that model, again, we can do, we can change the stiffness of the crease line to get a different kinematics. And also, we can change the unfolding length of the origami strain limiting layer to get different kinematics. And this is how we fabricate. We use FDM 3D printing, and then we attach the tubing to it, and then we heat treat it. And after heat treating, we get about 4 times higher strength. And TPU filament is pretty cheap, right? So and weight is pretty low. Cost of materials use $1, about $1, and you can do something like this. So you can do like multimodal grasping. So you have a gripper which can do this kind of grasping, and in the middle there's a suction cup. So if you want to use the suction, then you can use the suction. And if you want to use the finger grip, you can use the finger grip. Or if you want to do the collaborative gripping, you can do collaborative gripping. You can mix these kind of, because this is possible because we have a very large deformation of the gripper. And so shows the versatility, and also we can customize the force, we can customize the kinematics. So for example, we can do something like this, right? If you want a workspace with very, like this kind of round shaped workspace, and if you want something that can grasp much larger boxes, then you can just basically change the design and then 3D print, right? Which is, I think, the benefit of a soft robot, right? If you can design, you have a very large design space for soft robots. Large design space means large workspace. So you should be able to design many different types of soft grippers. Okay, and we actually, so this was 21, so it's already like 3 years ago. This was during COVID. It was an online challenge. This Robosoft, the gripper challenge is going on right now, but 3 years ago, it was the challenge was to grasp that big and heavy vegetable and very small and fragile vegetable, and also pick up a coin and then put it into that space. And we were able to do this very quickly, and I think we won the prize. And another morphing type of morphing thing is using snake tentacles. So this is similar to growing soft robot, right? This is, I guess, as a type of a growing soft robot. And this is it uses eversion, but what we are interested in is using the change of the diameter, right? It changes the diameter. And what we found was that actually in grasping area, about more than 90% uses suction cups, except that there's so many different types of suction cups. So what we thought was if we could just change the diameter of the suction cup, then we should be able to use it for different purposes. So if you have this kind of snail type eversion plus notches to be stable on that at that diameter, then you should be able to create a suction cup that can pick up like small diameter objects and also large diameter and high force objects, high load objects. So we created this video of picking up a Cheshire, large, and then change to small, and then we pick up like small, right? Well, a dummy application, but shows the effect of our gripper. And then we can combine both, right? We can combine the the diameter changing suction cup plus our deployable soft gripper. Then that means we have a larger type of materials that we can pick up. And then this is another. This was presented at last year's RoboSoft. So this is a deployable soft origami link. Basically, we wanted to build a deployable arm with using origami design. So design principle is based on Tachimura origami, and it's actually the key principle here. What we wanted to do was we wanted to build a very high payload arm. So to get a high payload arm, if there is this folds, then we cannot get a high payload because they will be all folding away. So what we did was we made this cylindrical buckling. So if you keep on applying pressure, all the joints buckles, and then now you get a pretty smooth surface. So a smooth surface means that you can get a high payload. So it goes out of the kinematic state, and now we are showing that it has a high payload in all directions. And then two parameters in the bending test, and you show that the variable stiffness equivalent flexure, we can actually see there is a buckling dominant phase and the pressure dominant phase. And as you can see here, the buckling side, the buckling front, and no buckling side and no buckling front. So if you compare the buckled ones and non-buckled ones, that you can see there is about 3 times difference in the the pressure that it can go. So it's buckles at 200 kilopascal. So cylindrical buckling effects of origami arm increases the rigidity to 12 times. And fabrication is done by heat pressing of the fabrics, and then we do stitching to reinforce the structure. And if we reinforce by stitching, we get 3 times more. And then we do like oven shaping. And then one issue here was that while it deploys, as you can see at the top, it doesn't like deploy straight. So if we add a tendon on the side, and if we actually pull the tendons while it's deploying, then you get this kind of pretty simple and neat deployment. So prevents the deformation during the deployment. And as you can see here, so front view and side view. So this is actually still, I think it's still an issue. So we would like to get rid of the tendons eventually. And this is the modeling. And so two applications. One is self-deployable rover. So we actually created a rover, and another is assisted robotic arm. So basically, it's a modular design. So we have, one arm. We can connect each arm. So you can see that from its initial compact size, deploys and forms a workable structure. Right? We are using the gas tank from the what's the gun, and 14 kilograms, and it's okay. So application real world, semi real world application is the rover is inside some cabinet and then comes out and then deploys and does that. And then we can also use it for assistive deployable robot arm. So it can be shrinked into like small size. It can be deployed, and they can become a arm. And now we are working on 3D printing of this self-deployable origami, and we are using a large-scale origami, which we print on a conveyor belt. So because we are 3D printing and then doing a pattern sheet fusing and then oven curing, it's more efficient way. And this is this was built to be intended to be a frame of a tent. So imagine if you have this kind of a small tent frame. If you attach a wheel, it will go to the camping area, opens up, becomes a tent. So that's a concept. It's not realized yet, but so we had a project with a tent company on this. So it just shows the feasibility of doing this. Some other things. These are our old, like back in 21. It was a shape-changing wheel, transformable wheel using origami patterns. We started. So actually, our work on origami started with this, our wheel that changes using origami shape. And we started using fabrics. So we originally used papers, and then we had captains surrounding the papers, and then now we switched to fabric. We started stitching at the time, and then we went to a bigger wheel, and then after this wheel, we went to a bigger wheel and higher payload. And eventually, what we did was we built a wheel that could actually switch change its shape from this kind of flat shape to large shape. And so we had to go through several procedures, and we are using fabric that actually goes into the tire, and we're using metal. So this fabric actually is inside tire fabric that goes into the tire, and then we were able to create a large actual size tire, and then we were able to test this. And so this one, again, this is not for like just storing, but this is for multi-purpose wheels. And also we worked on a Seokjun. I think he's here. Actually, so Ungbei, who's sitting behind, is the one who worked on our origami work. And this is deployable, again, using origami, very lightweight paper, base flat, foldable, lightweight, highly stiff robotic arm. So as you can see, we have a similar concept. It has to be lightweight, it has to be compact. It should be like foldable and deployable. So, but not in use, you keep it compact, and when you use it, you elongate it. It has to be pretty, very high. And this one, again, this was based on our origami design, morphing origami blocks. So we actually had this kind of idea of using papers, plus we had an idea of using torsional shape memory alloy actuators. It's very light, 6 RAM, almost real time, X times 2. And so this was published in TRO back in 21. Has a bistability. So we like to make use of bistability. We like to make use of buckling. So for soft robots, I think making use of those kind of properties like bistability and buckling it gives you nice features. And because we're doing that, so it's a intrinsic pair of torsional shape memory alloy is on uh, all the joints. So it's much more complicated than other origami designs where we use only single actuation. It has like a lot of actuators attached to it. It takes a very long time to build, but if we can automate this somehow, then as you can see, this was a deployable. It's another model for creating this kind of shape morphing design. Okay, so I guess so. This is a shape morphing workshop. So I'm sure everyone has different goals and different thoughts about shape morphing. For me, for our lab, morphing is for human environment robot interaction. So we want enough payload to be practical. We want it to be safe. We want it to be space efficient. We want it to have large workspace, lightweight. So it's not like soft robotics. I think we don't want soft robotics to be soft robot. We want soft robotics to be useful in the real world. And to do that, I think we need some what do you call conflicting characteristics, right? It has to be lightweight, but it has to have high payload. Right? It has to be compact, but it has to have large workspace. So I think one of the benefits or the advantage of soft robot is that we can do this kind of things that the current other robots cannot do. I mean, they can probably do this, but maybe we can do it better. We have to do it better to survive, right? So I think I think soft robotics area it's been booming for almost like 10 years now. I began when I started working on soft robot. Some people were not acknowledging this as a robot. So but now we are on the different. We are on a different what do you call risk, because there's a lot of soft robots, but now we have to find some useful application in order for our field to survive. That's what I think. Because if we keep on just building soft robots for the sake of a soft robot, and now I see sometimes reviewers saying, "Oh, this is not a soft robot." It's okay if it's not a soft robot. It's just gotta have different characteristics that traditional robots don't have, right? So that's what we should be targeting. We should be targeting like specific like application or specific features, at least something that other traditional robots don't have. And I think shape morphing is something that robots can definitely have advantage compared to traditional robots. So let's enjoy. And the ICRA 27, it's only 2 years and 4 months left for submission. Okay, so if you just started on a project, okay, 2 years later, submit it to ICRA 27, okay? All right, thank you. I'll see you guys.